today's session. Welcome all of you for the last session of this Power System Engineering NPTEL course. So today is the last session and we will revise all the concepts. We will not go through each and every concept because 2 hours is not sufficient time for doing that. So the best way to cover the entire course is through questions, because you will be taking exams and you will be solving questions in the exams and all the numericals. While doing those numericals, we'll be able to cover the concepts. So we are going to take all the 12 weeks important questions which will cover most of the concepts, and that's how we will wind up today's session. So I hope the slides are visible to you. Let us begin then. Okay. So I hope this is the last class, so all of you already know everything. This is the channel where you can get all the recordings, and also on the portal, the NPTEL portal, on the left hand side you will see one problem solving session tab. There you can find link to the Google Drive, and in that Google Drive you will have links for the recordings of all the live sessions as well as the PPTs used during these live sessions. So we will start with the week 1 question. So this is the first question. So in week 1 was mostly about the insulators for overhead transmission lines. In insulator, all the numerical questions are based upon similar concepts. Again and again, in all the numericals you will have to follow these steps. We have to write KCL at each node. Let's say there are total 4 insulators. So one is this, so second, then third, let's say only 3, and here the conductor will be there, because I am removing the conductor right now. And here so between each insulator we have insulator pin. So these are the string insulators. and between two insulator there is one capacitance, and also there is a capacitance between earth. This is called pin, and this is earth. So earth to pin also there is a capacitor. If this is C, then this is K times C. This is smaller. K is between 0 to 1. So we assume that this is E1, voltage across first capacitance, second capacitance, and third is E3. And V line to line voltage is root 3 times E1 plus E2 plus E3. So E1 plus E2 plus E3 is the phase voltage. If you multiply it by root 3, you will get the 3 phase line to line voltage. And now if we see voltage between this point and this point, let us call this as A and this is B. Between A and let's say this is O, this is also O, because everything is grounded, so everything is O. So between AO, this is also AO, this is also AO. So E1 and E1, voltage across both the points is same. They are in parallel. Similarly, if you want to find voltage between OB will be E1, OB will be this, same as this. So it is E1 plus E2. Now if you want to write out KVL at, not KVL, it is KCL. Let us first define currents. So this is I1, this is I1 dash, this is I2, this is I3, and this is I2 dash. So we write KCL at each of these nodes. So KCL at node A. So you can write I2 is sum of two currents, which is I1 and I1 dash. Now we have to write current in the form of voltage. You know current is voltage divided by impedance, and here impedance is 1 by j omega c. So current is V by Z, and Z is 1 by j omega c. So it is j omega c into V. So this is the current. So I2 across, so this capacitance voltage is E2. So it is j omega, capacitance is C, and voltage is E2. Now I1 is this. So capacitance is C, j omega C, and voltage is E1 plus, now this voltage across this KC capacitance is also E1. So it is j omega KC, not C. It will be KC into E1. So now j omega c cancels out. You will find E2 is equals to K plus 1 times E1. Similarly, we can write the KCL at node B also, and it will be I3 is equals to I2 dash plus I2, and this is equals to j omega c. E3 is equals to j omega c E2 plus, now voltage across this capacitance is E1 plus E2. So it is j omega kc into E1 plus E2. So E3 is equals to k E1 plus k plus 1 E2. So you can also write everything in terms of E1. So this will be k E1 plus k plus 1 square E1. So this will be k square plus 3k plus 1 times E1. So this is E3. Similarly, if one more is there, then we will write one more KCL. So we'll go through this question now. So here we have, it's a 3-phase overhead transmission line suspended from a cross arm of a steel tower by a string of 4 insulation suspension insulators, also called as string insulators. So these are the suspension insulators. So we have these suspension insulators, and the voltage across the second unit is 12 kV. Voltage across third unit is 16 kV. And we have to calculate the line voltage. Okay. Let me just write this part. Okay. Here you can see. So E2 is given as 12 kilovolt. E3 is given as 13 kilovolt. Now first thing, whenever we see this such any questions on insulators, we have to write the KCL equation at each node. Now we have here how many nodes? 1, 2 and 3 nodes. We have written A, B and C. So we have to write KCL at A, B and C. For A and B we have already written. So you will get E2 as K plus 1 E1 and E3 as K square plus 3K plus 1 E1. The same thing, E2 is this, K1, K plus 1 E1, and E3 is this, same, K square plus 3K plus 1. Here, because we know E3 and E2, so what we are doing, E3 is K E1 plus 1 plus K E2, and E2, this E1 also I can replace by E2, and E1 can be written as E2 by 1 plus K. So now this is in terms of E3 and E2, and both are known. So from here we can find out K. So E3 divided by E2 is equals to K plus 1 plus K square divided by 1 plus K. So this goes 4 by 3, and we can easily calculate the value of K using this quadratic equation, 3K square plus 5K minus 1. And you will get two values here, one is negative and one is positive. And so negative value is not possible for K because it's a value of capacitance, because K is multiplied. So Kc is a value of capacitance. Since C is always positive value of capacitance, so Kc has to be positive as well. Okay, so we will take the positive value, and also we know that K is always between 0 and 1. 1.8 is not the correct value, so we will go for 0.18. Now same, just as we had written KCL for the two nodes A and B, we can write the KCL for node C as well. This is J omega C E4 is equals to J omega C E3 plus J omega KC into E1 plus E2 plus E3, which is written here. So E4 is equals to KE1 plus KE2 plus 1 plus KE3, and E2 we know it is 1 plus KE1, and E3 is K square plus 3K plus 1 E1. So if we substitute E2 and E3 here in terms of E1, finally you will get this K cube plus 5K square plus 7K plus 1. Sorry, 6 this is k cube. So 2k square plus 4k. K plus k square plus 2k plus 1 plus k plus k square. There is a mistake here. So it is k and this is k plus 1 into k plus 1 plus k into k square plus 3k plus 1. So this becomes k plus k square plus k plus k square plus k cube plus 3k plus 3k square plus k plus 1. So this becomes k cube plus 5k square plus 3k 4k 5k 6k plus 1. Okay, so this is correct. This should be 1 plus k into k. Okay, so this is correct. So from here we already know E2 and E3, and k we have already found, it is 0.18, so we can substitute here k. So E2 is 1.18 E1, and E1 we can find because E2 is 12 kV. So this is E1, this is E2, E3 already known. E4 also we can find out by using this, so it is 22.85. Now we want to find out the line voltage, so we need to add all these 4 values and then multiply it by root 3, so we'll get the VLL. You can also find out the string efficiency. Right? How can you find out string efficiency? So it will be the string efficiency here will be n times, n is the number of these units or pins, E4 divided by E1 plus E2 plus E3 plus E4. It is 4 multiplied by E4 is how much? 22.85. Opposite, it is E1 plus divided by n into E4 multiplied by 100. So E1 plus E2 plus E3 here is compound now 10.169 Let us calculate 10.169 plus 12 plus 16 plus 22.85. So this is 61.019 divided by 4 into 22.85 multiplied by 100. This is string efficiency. This is only 66.67%. The string efficiency is quite low here, we can see. So for increasing this, and why is this string efficiency low? Because the voltage across each insulator is different, and we see the lowest insulator is stressed the most. It has to be designed for 22.85, and that's why all of them will be designed for 22.85 for a standard value, to have standards. So that will be, so above insulators are not utilized, they are underutilized. We can increase the string efficiency by adding that guard wire. Then there is one more capacitor here. There can be one more here also. So then in KCL, one more current will come here, and that will be like this. Like this. So to remove the effect of this capacitance. So if we cancel these two, then current is same. The current I4 will become equal to I3, and I3 will become equal to I2. If current is same, capacitance is same, the voltage will also become same. So that is the ideal case, although we cannot perfectly nullify that. But in ideal case it is possible, because in ideal it is possible, but practically it is not possible because we have standard value of capacitances. Let us move to the next question. Now it is on the week 2, where we discuss the cable, underground cables. So it is about a single core cable and 45 volts, 45 kV, and it's a 3-phase. So conductor diameter is given as 2 centimeters, so small r is 1 centimeter. So it is something like this. We have this conductor here, radius, this is r, and this is capital R. So this is a sheet. Dielectric material. It is, so this is 5, capital R is 5. It is desired to maximize stress by using 2 inter sheets. Now what is being done here? This is outer. Here we are adding 2 inter sheets. And it is desired to reduce the maximum stress. So we want to maintain the maximum stress by minimum stress. As constant. Emax 1 by Emax min is equals to Emax 2 by Emax 1 is equals to Emax 3 by Emax. Sorry, this is E min. This is also E min. E min 2 and E min 2. As a result, R1. So this is R, this is R1, this is R2, and finally this becomes capital R. So R1 by R is equals to R2 by R is equals to capital R by small r2. This, let's say it is alpha. So if we take the product, this is R1 by R. So capital R by small r will come out to be alpha cube. And from here we can find out alpha. How much will be alpha? It will be r cube root of r by r. So it will be 5 cube root of 5, and it comes out to be 1.71 centimeters. So here, from here we can find out r1 and r2 also, because r is known. Let me write, and as I make it slant. So r by r is equals to alpha cube, and alpha is 1.7 centimeters. R1 is equals to r into alpha, and r is 1, so r1 r is 1, so r1 is this, r is 1, and r2 is r1 alpha, so 1.71 square (2.92). Capital R is 5 centimeter. Okay, now here what we have to find out? We have to find out the ratio of maximum stress without and with intersheath. So if there is no intersheath, maximum stress will be P divided by R ln R by R. If this is at V, then this is at 0, so V minus 0. Now here, if it is, this is V, this is at V1, this is V2, and this is at 0. So we can write V, because so this is, we can write V minus V1 by R ln R1 by R. This is equals to V1 minus V2 by R1 ln R2 by R1, and this is equals to V2 divided by R2 ln R by R2, and all these are alpha. Same thing is written here. So R1 by R is equals to R2 by R is equals to capital R by small r2 is equals to alpha. From here we find out alpha, you can find out, and alpha although here it is not required, but it comes out to be 1.71 centimeter. So from there we can also find out the Emax, because voltage is already given, it is 45 kV. So we can find out the maximum stress also. Emax will do that. So here we want to find out the ratio, right? We want to find out the ratio of maximum stress without and with intersheath. So without intersheath is, I already told you, V divided by R ln capital R by small r. And capital R by small r is this alpha cube. So that's why it is alpha cube here. So it becomes V 3 ln 3 R ln alpha. And V minus V1 by R ln alpha, this is also same for same dielectric stress. So V ln alpha will cancel out. So from here we can easily write two equations, and we can get V is R into V1 by R plus V2 by R2. And another equation, so first one, using this you can write this, and using these two you can write this. So V1 by R1 is equals to V2 into 1 by R1 plus 1 by R2. So you can multiply R1, so it will be V1 is equals to V2 plus R1 by R2 into V2, and R1 by R2 is 1 by alpha, so it is V2 into 1 plus 1 by alpha. So V1 is written in terms of V2. Similarly, we write V also in terms of V2. So now V from this equation, it is V1 plus R by R2 into V2. And V1 is this V2 into 1 plus 1 by alpha, and V2 into R by R2. From here we have to use this. R by R2 we don't know directly, so what we can do, multiply either by R1 or capital R. So capital R, if we multiply and divide, then we know R2 by capital R, this is 1 by alpha, and we also know this because it is alpha cube. So capital R by small r2 is alpha, and this is alpha cube, so it becomes, so R by R2 is equals to R by capital R and capital R by small r2. So this is 1 by alpha cube, and R by R2 is alpha. So this becomes 1 by alpha square. The same thing is written here. So this becomes V2 into 1 plus 1 by alpha plus 1 by alpha square. So Emax will be V2 divided by R2 ln alpha from here. Okay. Am I audible? Oh, sorry, there was some problem. Let me share the screen again. I hope it is visible. Yeah. This technology also puts us in trouble many times. Let us move ahead. So we are talking about this. Yeah. So V2 divided by R2 ln alpha. So this is, and V2 we can write in terms of V. It will be V divided by this 1 plus 1 by alpha plus 1 by alpha square. And R2 we can write as R divided by alpha. So R divided alpha goes up. So this is when intersheath is used. Now we are going to divide this by this. So V by 3 ln alpha and divide by this. So V alpha, V cancels out, ln alpha cancels out, and capital R by small r is alpha cube, so alpha cube by 3 into this. So ratio comes out to be alpha square plus alpha plus 1 by 3. So this ratio is entirely dependent only on the alpha, and which is the ratio of capital R by small r. So this is 1.878. Next V. So this is V. Here is, so this transmission and reflection coefficients. For voltage and current. We saw voltage and current as say there are two lines with different impedance, and this is the junction.
Yes, sir.
And here
Yes, please go ahead, sir.
this is forward. So some is transmitted and some is reflected back. So we backward. Like transmitted voltage is a sum of V
हो हो
forward and V
हो
back.
मी पाठवतो 22-23 ला पाहिजे ना तुम्हाला.
Transmitted current is V
हां मी
forward
स्टॉप
plus
फक्त
I
स्टॉप
backward.
स्टॉप कन्फर्म करायचा होता म्हणून उत्तर दिलं नव्हतं. तर हां मग मॅडम आता एक 4-5 दिवस नाही काय मग येतील काय 22 पर्यंत येतील 21-22 पर्यंत. हां सांगतो मी त्यांना. ओके सर थँक्यू. हां बोला. हां बोला. हां बोला.
There is some problem with the laptop. Just a minute. Let me restart. So V transmitted is V forward plus V backward, and current is similarly I forward plus I backward. And this is, let's see, this is ZC1, characteristic impedance of the second line is ZC2, this is junction. So this is V forward divided by ZC1, and I backward is minus V backward divided by ZC1, and I is V divided by ZC2. So this we can write as V forward divided by backward V ZC1 divided by ZC2. And now from these two equations we can write 1 plus ZC1 divided by ZC2 is equals to 2Vf. So the transmission coefficient for voltage is V divided by V forward, and this is equals to 2ZC2 divided by ZC1 plus ZC2. Now if you want to find current transmission coefficient, then this will be I divided by I forward. This is V by ZC2, V by ZC1, Vf. This is ZC1 divided by ZC2 into tau V. So this will be 2ZC1 divided by C1 plus ZC2. So this was transmission coefficient. Similarly, if we do 1 minus 2, we can find out reflection coefficient also. So it will be 1 minus ZC1 divided by ZC2 is equals to 2V backward. And so rho V is equals to V forward. And V backward is V by 2 ZC2 minus ZC1 divided by ZC2. And V forward we have already calculated this. This is V by 2 ZC1 plus ZC2 divided by ZC2. So this is ZC2 minus ZC1 divided by ZC2 plus ZC1. Similarly, current will be I backward by I forward. This will be V minus V backward by ZC1 divided by V forward by ZC1. This is minus rho V. So here the question is refraction coefficient or transmission coefficient of voltage and current at the load end of a short circuited line. So in this case ZC2 is 0. Yes, ZC2 is 0. If we substitute 0 here, so this becomes 0. And if we substitute 0 here, then it becomes 2. Similarly, you can also find the reflection coefficient. For voltage, ZC2 is 0, it will be minus 1, and current is simply minus times rho, so it is 1. So this is the next question. So it is continuation of that only. But here now we have one transmission line having surge impedance of 225 ohms. So this is ZC, let's say ZC, and it bifurcates into two branches of surge impedance, 100 ohm, and another is 150 ohms. Let's see, this is I1, V, I2, voltage is same. Here we can again write the same equation. And this is only v. So v here is v forward plus v backward, and this is equals to I. And I1 plus I2 is equals to, and this is v forward zc minus backward, and this is v by zc1 plus v by zc2. This is v into zc1 this is Vf minus Vb multiply Zc here. Similarly again you can do add these two and you can find out tau. Here we have to calculate the voltage magnitude across the first branch and the current in the second branch. So V and I2 you need to find out. So once V is known, I2 can be found out easily. So I2 is V by Zc2. So we need V. Need to find out V. So V you can find out from here. So find out, add these two. So this will be V into Zc divided by Zc1 Zc2 divided by Zc1 plus Zc2 plus 1 is equals to 2Vr. Vf is known, this is 230 kV. So from here you can find out V, it is 2Vf divided by this Zc divided by Z1 plus Z2 plus 1. It's same thing written here also. So V this is and I1 is simply this. This is I2 V by Zc2. Okay. So next is on corona. We need to find out total corona loss using Higgs formula. Rough weather condition for 132 kV 50 Hz 3-phase 175 km long transmission line consists of 3 1.6 cm diameter standard copper conductor arranged in a 3.5 meter delta. Assume air temperature to be 26, barometric pressure 750, surface irregularity factor and dielectric strength is also given. So from here we need to find out rho air density factor. So this is 0.392 divided by 273 plus T, the temperature. This is 0.392 multiplied by 70, 750 divided by 273 plus 26. .983 air density factor, and this is surface irregularity factor, and dielectric strength of air G is also given 21.2 kV RMS per centimeter. Also assume that the disruptive critical voltage is 0.8 times the disruptive critical voltage for fair weather condition. So first we have to calculate disruptive critical voltage for fair weather condition, and then VD dash will be 0.8 times VD. And we need to see the phase voltage should be more than the critical disruptive voltage for corona loss to occur. Now let us find out all these values. So delta we have already found 0.9833, and V naught under fair weather condition is G naught delta M naught, which is already given. Surface irregularity factor R is already known. R is this, D is 1.6 centimeters, so R is 0.8 centimeter, and capital D is 3.5 meters, so 350 centimeter. So this is 21.1, 0.98833, 0.86, 0.8 R. This is R, M naught, delta G naught, ln capital R by small r. So this comes out to be 86.80 kV RMS, and VD naught is 69.44, and it's already given. V line voltage is 132. So 132 by root 3 phase voltage is equals to, and this is equals to 76, and which is greater than VD dash. So there will be a corona loss. However, if this value is less than VD naught, then there will be no corona loss. In that case, corona loss will be 0. So always, whenever corona loss is being asked, always first of all check whether V phase is greater than VD naught. If not, then loss is 0. So now here we have phase voltage greater than the critical disruptive critical voltage. So we need to find out the loss. So this is 3 into length of the transmission line in kilometers. 244 by delta, 50 plus frequency is 50 Hz, plus 25 R small r by capital R or D, V phase minus critical disruptive critical voltage multiplied by 10 to the minus 5. So this is the corona loss. So next week is the sag and tension. It was discussed in this week. So we saw what will be effect of the wind speed and ice loading. So wind speed, we assume that it acts horizontally. So maximum problem will be when this wind speed is perpendicular to the weight. So resultant sag will be like this. So in vertical sag will be in that case as cos theta. So this is theta. So wind pressure is given of the project area with ice coating of 1.5 mm. Span is 250 meters. Transmission line with a conductor diameter of 20 mm weighs 820 kg per mm. You have to find, and the ultimate tensile strength is given as 7000 with a safety factor of 2. So tension is 7500 divided by 2. Yes, tension is this. Where diameter is 2 centimeters. Thickness of ice coating is 1.5 centimeter. So this was the diameter. This is the diameter of conductor. And this is ice coating over here. This is thickness T by 2 overall T, and this is total D. This is thickness is T. This is also T. So wind is acting like this. So wind pressure is 42 kg per meter square. So area we have to take, so per unit length. So only this length is covered. If we take so conductor is like this, and if we take this as only 1 meter, let's say 1 unit, so this area we need to find out, which is this rectangle. This area is length into breadth. Length is 1 meter and breadth is d plus 2t. So if you multiply it with this wind pressure, so we will get 42 multiplied by 2 plus 2 is 4 plus 2 plus 3 is 5 kg per meter. So this is 2.1 kg per meter. conductor weight is already, it's 0.82 kg per meter. And ice, so we have to find out this. The weight of ice to find out. This is d plus t, pi d plus t square minus pi d square. Weight of ice is 910 kg per meter. So to multiply it with the area of the ice. This is correct. This is pi into d square 4 plus t square plus dt minus pi d square by 4. So this is t into d plus d into pi into rho. You will get this pi rho ice into t into d plus t. So you will get ice loading, that is 1.5 kg per meter. Wind loading is also available. So total loading will be this. This will be V plus W ice and this will W wind. And this is at angle theta. So we can find out omega is omega naught plus omega I square plus omega wind square. So this is 3.13 kg per meter. So this is the maximum sag. Maximum sag here will be omega naught L square by 8t. If it is asked what is the vertical sag, then it will be S cos theta. We need to find out this theta. Theta is tan inverse you can calculate. So S into cos theta here vertical sag comes out to 5.18 meter. Next we entered into the domain of distribution system analysis or distribution network analysis. The sample 3-bus distribution network is given. Below with line data and load data shown in figure. So base VA is 1 MVA and voltage base is 11 kV. And we have to use the method 1 to find out the bus voltage by located at bus number 3 after second iteration. Consider all the bus voltages as 1 plus J0 as the initial guess. So it is 1 angle 0. Line impedances are given in ohms and kilowatt. This is in kilowatt and kVAR. So let us do the method 1. So here we are assuming that all the voltages are 1 angle 0. So what we will do here, we will first of all find out, first of all we have to convert this into all these ohmic values into per unit, and this also everything into per unit. So kV base is given, MVA base is given, Z base is kV square by MVA base 121. So divide Z1 and Z2 by this value, we'll get this in per unit. Similarly, divide this MVA base is given as 1 MVA. So divide this by 1000. 8.2 plus J.1. 0.1 plus J 0.08. And is already given. We have to start with flat start. Initial guess is flat start 1 angle 0. So now with this assumption, we know that P, let's say Q, which is apparent power, is equals to VI star. So I we can write as P minus JQ divided by V star. So this will be used here again and again, and we have to find the current here. Initially we have assumed that voltage is 1 angle 0, so we can, this will be same as PL2 minus JQL2. Similarly, I2, I3 we can write PL2 minus JQL2 and PL3 minus JQL3, which is this. So these are the load currents. Now we can find out the branch current. So I2 will be same as I3 and I1 will be I2 plus I3. I2 plus I3. So this we can calculate. So now that we know the branch currents, we can find out the voltages. So V2 will be V1 minus I1 into Z1, which is this. Now V3 will be V2 minus I2 into Z2. So now we have to use this updated value of V2, not the value used for flat start. Now use this value. If you will use this value, then number of iterations will increase. So use the most updated value and then we'll find this as V3. Now these are the new voltages, new node voltage. Again, for iteration 2, first of all, we will find the load currents and again the line currents. So first the node current and then the line currents. So these are the voltages we have calculated, V21 and V31, and the load currents will be PL2 minus JQ2 divided by V21 star. Similarly, PL3 minus DQL3 divided by V3 1 star. You will get load currents I2 to I3 to. Branch current is I2 is same as I3 and I1 is I2 plus I3. So after two iterations we have to report the voltage. You can easily say V2 is V1 minus V1 Z1, V3 is V2 minus I2 Z2. So V2 is V1, V1 is use this, V1 is 1 angle 0 and I12 is this. So you will find V2. Now use this value of V2 for calculating V3. And I2 as this one. So you will get this 0.9880. So question was to find out bus voltage magnitude. So bus voltage magnitude after second iteration, third bus voltage magnitude after second iteration is this. And the next question. So this is based upon the method 2. Here only the magnitude is known but the angle is not known. Line data and load data is given. Base V is same. The same question only is to be done with the method 2. And after second iteration we have to find out the active power loss in the branch 1. So method 2, V1 is 1 per unit magnitude, and in this second method we don't need the angle information. So first it is based upon the net load. So we make the net impedance model for each branch. So we see at P2 what is the net load connected at bus 2. So P2 will be, and also it has to incorporate the losses. So initially it is assumed that the losses are 0. It is based on the, so first one is, method 1 is assuming initially flat start. So it is giving two information, one is for voltage magnitude and angle. So both are considered to be known, 1 angle 0. In second method, we are using equivalent impedance model. For each line, and we are assuming that the initial gas is voltage magnitude is 1 for bus 1 and losses are 0. So since the losses are 0 for initial gas, P2 will be PL2 plus PL3 plus loss in line 2, 3, which is 0 initially. Similarly, we can also write for reactive power. Now we have to use this formula where A1 is P2 into R1 plus Q2 into X1 minus 0.5 V1 square, and D1 is A1 square minus R1 square plus X1 square into P2 square plus Q2 square root. You can find out A1, and A1 will always be negative of D1. The A is negative of D. So V will be D minus A. So it will be, we can say twice D. Take a root. Because D will always be, if A is negative, D is always positive. Similarly, you can also calculate A2. So P3 R2. And P3 is same as PL3, so there is no line beyond that. Same as PL3. So both V2 and V3 are known. Now since V2 and V3 are known, we can find out the losses. How to find out the losses? We can do I square R. I we have already calculated to much. P minus JQ by V star. This is I magnitude is P square plus Q square divided by V. Now multiply by R also. Okay, from here we are getting this expression for loss in line 1. So it is R1 into P2 square plus Q square by V2 square. Similarly Q1, when P lost 2 and Q lost 2 also we can count. Now for the second iteration, these are the initial value of losses. So P2 is PL2 plus PL3 plus P loss 1. Q2 is QL2 plus QL1 plus Q loss 1. And Q3 is only QL3. And P3 is PL3. Again calculate A1 D1 and then V2, A3 D3 and V3, A2 D2 and V3. So you can find out loss in branch 1. So this was the question. We have to find out the loss, active power loss in the branch 1. This is the total active power loss in the branch 1. Multiplied by 1 MVA to 2.8 megawatts, kilowatts. Yes, next question. This is on ring names in distribution system. The question is, a DC ring gain distributor is supplied through a feeder AB and is loaded as shown. Loads are tapped off at point C, D, E and F. An interconnector is placed between C and E. E is the feeding point and is maintained at 380 volts. Resistances per 100 meter length of AB, ring distributor and the interconnector are we have to find out the current flowing through the interconnector. See this current. So what will be the total current? This is I. So loads are being tapped. This is I. So I 20, 30, 20 is 20 plus 30 plus 10 plus 40. It is 100 amperes. So this is I. This is it's I minus 20. This is I minus 40. Let's say this current is X. This is I minus 20 minus X. This is I minus 20 minus 50. I minus 90. So this is I. Let's say X current flows here, Y flows here. One equation we know that X plus Y is equals to 100. Now this is X minus 20, X minus 50. So this is Z. This is Y minus 40. Now we can write case KVL in these two lines. So write KVL in these two loops. First one is I2 into X you can see here this is 1 ohm, 1 to 2 ohm. So 0.2 into X plus Z into 2.5 into 0.2 is equals to Y minus 40 into 1.5 into 0.2 plus Y into 1.5 into 0.2. So this is 0.2, 0.2, 0.2. X plus 2.5 Z is equals to 3Y minus 60. Now write in this. So X minus Z minus 20 into 0.2 into 2 plus X minus Z minus 50 into 0.2 into 2 is equals to Z into 2.5 into 0.2. This is the second equation. The third is this. So you have 3 variables and 3 equations. If we solve, it is substitute for y from this equation, then it is 300, because in this equation there is no y, so it will become 3 into 100 minus x, which is 4x plus 2.5 that is equals to 240. Now solve these two equations, add these two, and it is formed is equals to 380, and z is equals to 100, and z is 100 by 9. So x and y also can calculate. So everything is known. What was the question? Determine the current in the interconnector. It is z. Z is 11.11 amperes. The next question is on capacitance, the use of application of capacitors in the distribution system. So we have two capacitors. In two ways we can use capacitor in the distribution network or even in transmission network. One is series, another is parallel. As shunt component, and this is series component. This is shunt is primarily the main aim is to reduce the losses. And series is to boost voltage. Star connected 440 volts. So this is the question. It is star 440 volts, 50 hertz, induction motor, line current of 20 amperes, 0.85 pf. So new pf. Find the rating of capacitor by kV. You can see capacitor is providing active power. So if this was the power angle triangle before, SP is same, this is Q, and after adding capacitor becomes this. This is the QC. So initial one was equals to this. We want this. So P you can calculate from here. 20 amps. So power is root 3 VL cos phi. This is the root 3 root 2 VL. Star connected. And minus 20. Phi is cos phi is 0.84. So Q we can calculate as P10 5. Similarly here also you can find the QC will be Q1 P10 5 1 minus P10 5 2. This is P load and this is Q load. P10 I1 and this is P10 phi 2. If you subtract these two you will get QC. So difference will be provided by capacitor. Next is the capacitance of each capacitor in microfarad. So it is star connected. The QC is known, it is 3.778. This will be C. So first I will find out Q per phase. And we know Q is equals to V phase square by XC. And V phase is V line by root 3. And XC is 1 by 2 pi FC. And this is Q phase. Substitute all the values and calculate the per phase capacitance. Week 10. So week 10 onwards it was line frequency control. So the question is, there are two generators rated at 775 kV and 225 kV and both are operating in parallel. Both the generators have same number of poles and same no load speed. So we have Okay, so let's say this is generator is 3% and this is 5%. This is generator 1, generator A, this is generator B. So governance setting of the machines are such that they have 3% and 5%. This is 3% and this is 5%. Determine the kilowatt of load shared by generator B at steady state for a total load of 500 kilowatts. So total load is 500 kilowatts. Let's say the load shared by generator B is change the color. Let's say this is X. So this will be something 500 minus X. So you can use the property of similar triangles here. Okay. This is some frequency. This is some frequency F naught. So this is F naught and this is some frequency F and this is droop, 5% droop. This will be how much? 5% droop. 1 minus 0.05 F. This is 0.95 F naught and this one is 0.97 F naught. Now we have to use this. So this was F. F naught minus F divided by 500 minus X is equals to F naught minus 0.95 F naught is equals to this is 775. This is 775. And this one is 225. So this is one equation. Then next is F naught minus F. So first we saw this. So let us get this A, B, C, D, E. So we did this is AE divided by DE is equals to AB divided by BC. This is for generator 1. Similarly for generator 2 also we have to write. So it is f0 minus f divided by x is equals to f0 minus point, this is 0.95 f0 divided by 225. We want to find out x. So this is 0.03 f0, 0.05 f0. So divide both the equations. What will you get? X divided by 500 minus x is equals to how much? 0.03 f0 divided by 775 multiplied by 225 divided by 0.05 f0. X divided by 500 minus x is equals to 225 into 3 divided by 775 into 5. So x here will be 74.18 kilowatts. Similarly, we can also then rest is 500 minus x. Remaining 500 minus x by generator A. Generation of generator A. G A. Kilowatt of load shared by generator B at steady state we have calculated. Next is determine the steady state speed deviation. So delta F, which is F minus F naught divided by F naught. Because speed is proportional to frequency. So frequency is proportional to speed. So for that we need to find out F here. So you can write F, you can find out in terms of F naught. X is 74.18 and 05 F naught divided by 225. F is 0.983515 F naught. For F naught minus F from here you can write equals to 105 and divided by 225. So F naught minus F divided by F naught is equals to the answer 105 multiplied by 75 divided by 225, so it will be 1.64%. 11, make 11. So load frequency control. For an isolated generating system with local load shown, it is observed that delta PL is minus 0.15 per unit. It brings about delta omega of 0.25 per unit. In steady state, find the value of R in per unit. Take delta PL as 0. This is delta PC. So this is simple. This is delta omega. So here delta omega by R, delta PC minus delta omega by R multiplied by 1 plus S minus delta PL whole multiplied by 10S plus 1. This is delta omega. From here you have to find out delta omega. This is 0 minus delta omega by R into S plus 1 minus so delta omega. This is S plus 1 minus delta PL. This is multiplied by 10. 10s plus 1 minus 10 divided by 10s plus 1. Delta PL is equal to delta omega. Delta omega will be minus 10 10s plus 1 delta PL divided by 1 plus 10 divided by x plus 1 s plus 1 10s plus 1. In steady state, limit s tends to 0. So this is 0, this is 0, this is 0. Delta omega steady state is equal to minus 10 delta PL 1 plus 10 by R. So R is 2 per unit. So this is next. question here is different. It is asking what should be delta PC to make delta omega 0. Now delta PC is not 0. In steady state we want delta omega to be 0. So what should be delta PC? So we already know that delta PC should be equal to delta PL. That again we need to solve same thing. So this multiplied by this one is this. So minus 1 by into delta omega plus delta PC multiplied by 1 by 1 plus S minus delta PL multiplied by 10 divided by 1 plus 10S. So we will get this. In this, if we substitute limit as tends to 0, and this is 0, this is 0, this is 0, this is 0, so it becomes minus 10 by 1 plus 10 by R into delta PC minus delta PL. Delta omega is 0, so for this to be 0, delta PC has to be equals to delta PL. So last question for today, then we'll wind up. Last question is, consider a 50 Hz 2 area power system connected via tie line. So this is a 2 area This is for a simple isolated unit system. Minus delta PL divided by D plus 1 by R. If there is no speed response, then it is delta PL by only D. And in multi-unit system, multi-unit isolated system, it will be delta PL divided by D plus REQ. Equivalent, where 1 by R equivalent is equals to 1 by R, so on to 1 by R on a common system base. Okay. Here it is said there is a load curtailment of 50 megawatt in area 1. So load curtailment is negative change. So delta PL is equals to minus 50 megawatt delta PL1, and delta PL2 is equals to 0. No control action is activated. To find out the steady state frequency, delta P type, all these steady state values need to be found out. So this is R, D and base MVA. So base MVA is same. So when base MVA is same, A is minus 1. And since delta PL2 is also 0, so delta F will come out to be delta minus delta PL1 divided by d1 plus d2 plus 1 by r1 plus 1 by r2, and d1 and we can substitute all the values. This is minus 50 divided by 500, so delta PL in per unit. Minus 0.1 divided by 0.8 plus 1 plus 0.04. And this is, even if you don't remember this, so you remember these basic equations. So we have 4 equations. So one is delta P max 1 minus delta PL minus delta P tie is equals to d1 into delta F. Second is delta P max 2 for area 2 minus delta PL. So this is area 1, this is area 2. P tie 1, 2 is coming out of area 1 by going into area 2. So this is addition here for area 2. For area 1 it is subtracting and it is adding into area 2. So delta P max 2 minus delta PL2 plus delta P tie 1, 2 is equals to d2 into delta F. And we also know from isolated system that P max 1 delta P max 1 is equals to minus delta F by R1 from the Droop, the governor Droop control, and P max 2 is minus delta F by R2. If we substitute these two here, we will get this minus delta F by R1 minus delta PL1 minus delta P tie is equals to d1 delta F. Here delta PL2 is 0. So if we add these two equations, this will cancel out delta P tie and we will get delta F is equals to minus delta PL1 divided by d1 plus d2 plus 1 by r1 plus 1 by r2. So this will be delta F in per unit, multiply it by 50, it will be in hertz, and then add it to F naught. So the saying load was reducing, that's why frequency is increasing. So next question was, what is delta P tie? So delta P tie we can calculate from here. So delta P tie is equals to delta F into d2 plus 1 by r2. Delta F is known, these two values are also known, you can calculate. Similarly, delta P max 1 is equals to minus delta F by r1, and delta P max 2 is equals to minus delta F by r2. And similarly, PL1, P load 1 is equals to d1 delta F. P load 2, considering frequency sensitivity, it is d2 into delta F. So all these parts are solved. So you can go through all the questions for all the weeks once again, and if you have any doubt, you can post in the discussion forum, or you can also write in the comment of this video link. So all the best for your exams, and thank you for joining.